All right, so today let's go ahead and start our discussion on Lewis theory. So whenever we start to consider chemical phenomena, one of the things that we want to think about is that a lot of this is driven by electrons, specifically valence electrons. Whenever valence electrons are shared or transferred, a lot of really interesting things start to happen. So for instance, whenever electrons are transferred from one atom to another, this is whenever we get an ionic interaction, or we can get an ionic bond, and then we have a cation, so the species that's losing its electron, and then the species that's gaining the electron, the anion, can start to interact. And these positive and negative entities interact through electrostatic forces. Now, if the electrons aren't physically transferred, but if they're shared, then this is whenever we would get a covalent bond. So there's different extents of sharing, and that's what we were kind of looking at whenever we were talking about there being polar covalent or non-polar covalent bonds. So the greater the difference in electronegativity, the more the electrons are going to tend towards the more electronegative atom. But throughout all of this, what's going on, whether the electrons are actually being transferred or if they're just being shared, is that we're trying to get to a stable electron configuration, noble gas electron configuration, complete that octet. We want to try to get 8 electrons around those species. So let's go ahead and start by looking at Lewis symbols. So a Lewis symbol, what we'll do is it's a chemical symbol. And whenever we write out the abbreviation for instance, let's look at silicone here. Whenever we write out Si, okay, so what that indicates is 1, that we have 14 protons. And then it also indicates that we have 10 core electrons. So it's more or less telling us that we have all of the core electrons. So the electrons that are representative of neon. And then what we'll do is we will place dots around that symbol to represent the valence electrons. So whenever we're drawing Lewis symbols and we're considering valence electrons, we're only considering electrons from the s and p orbitals. So here, silicone has 4 valence electrons. So there's 2 different schools of thoughts for adding these valence electrons on the Lewis symbol. One is to add a single electron to each side first. The other would be to try to go about it in the same way that we did for the orbital notation, and that you'd want to pick one side to be your s orbital, fill that up first, and then singly occupy the orbitals from there. So depending on what we're trying to do, usually if I'm drawing a Lewis symbol by itself, I would tend to probably use this method where I have fill up the s orbital, then the p orbitals. But as we start to draw Lewis structures later on, this one may be a little bit better for seeing how things are going to bond. So let's go ahead and consider our first Lewis structure here really quick. So whenever we're talking about a Lewis structure, this is more or less combining 2 or more Lewis symbols. So here we're going to consider an ionic compound. We're going to look at sodium chloride. So here, this is whenever we're going to actually show the transfer of electrons. So if we consider sodium, sodium has 1 valence electron. And then if we were to consider chlorine, chlorine has 7 valence electrons. So what we'll see is that in this case, if sodium were to give up its electron, so if it loses its electron, sodium can obtain a noble gas electron configuration. It will have no valence electrons, but it will have a noble gas electron configuration. Whereas if we were to look at chlorine, if it gains that electron from sodium, it's going to form an anion. So let me put that electron from sodium on there really quick. So we have our anion, and it has a negative charge. So the Lewis structure for this ionic compound is the cation sodium and then the anion chloride. So this would represent some electrostatic interactions between that positive and the negative charge. But what we're going to see is that we're trying to complete the octet. So if we look at chlorine, notice how we have 1, 2, 3, 4, 5, 6, 7, 8 electrons around chlorine. So this is an example of an anion that has a completed octet and has its outer orbitals full. So this is a stable ion. So let's go ahead and look at the case of a covalent bond whenever electrons are actually being shared. So if we consider hydrogen, so hydrogen has 1 valence electron. And if we were to consider chlorine, chlorine has 7 valence electrons. Okay, so what we'll see is that if these two are able to share electrons, these two right here, then chlorine would be able to have a completed octet, and hydrogen would be able to have a filled outer orbital as well, okay? Because if you think about hydrogen obtaining a noble gas electron configuration, well, the closest noble gas to hydrogen is helium, and it has the electron configuration of 1s2, so it has 2 electrons in the s orbital. So if we were to consider this, let's go ahead and take away hydrogen really quick. We can see that chlorine right here has a completed octet, so that's stable. And then if we were to take away chlorine and all of its lone pairs, except for the electron that's being shared with hydrogen, we can see that hydrogen has a completed octet. Well, we really want to say that it has its outer orbitals filled and it has a noble gas electron configuration, because hydrogen does not get an octet. So another way that we'll draw this, instead of having these 2 electrons here, so what we'll do is we'll draw it with a bond. Okay, so that's, the bond is just a straight line. We'll go ahead and draw our lone pairs on here. But this straight line right here, this is a bond. And this shows us that we have 2 shared electrons. All right, so let's go ahead and finish up this lesson by drawing a few Lewis symbols, and then next time we'll really start to get into drawing some more Lewis structures. So as you're going through and drawing these Lewis symbols and thinking about the number of valence electrons, remember that for the Lewis symbols, we're only interested in the s and p electrons, okay? So don't include any of the d electrons. So for instance, let's do nitrogen and phosphorus together. So nitrogen has 5 valence electrons. Okay, so its Lewis symbol looks just like that. Then if we were to consider phosphorus, that's directly below nitrogen. So it's going to start to be, we're going to start to notice similarities in things that have the same number of valence electrons are going to behave in a similar way, because they're going to interact in the same way in which how many electrons they need to obtain or give up or share to complete its octet. So why don't you guys go ahead and finish the Lewis symbols for the rest of these, and then we'll try to check these next time.